Hello everyone, welcome to this lecture. In the last lecture we studied excitation of a structure using a vibration shaker. In shaker testing, random signal and its variants are widely used for FRF measurement. Before we study FRF measurement with shaker using random signals, let us first of all see in this lecture how FRF can be estimated using random signals. Therefore, the topic today is FRF estimation with random signals. A brief outline of the lecture is as follows. First we will define what is random signal, and then we will try to explore that how to obtain frequency domain representation of a random signal. Then we will define autocorrelation function, autospectral density and autospectrum, and then we will also define cross correlation, cross spectral density and cross spectrum, and then in the end we will look at basically FRF estimation using estimates of auto and cross spectrums. So let us first of all define what is random signal. So a random signal is not a deterministic signal, right? Its future values cannot be predicted precisely. For example, earlier we have studied harmonic signal and periodic signal. For example, we have this signal, say a sine signal like this. So this is a deterministic signal, okay? This is a deterministic signal, and it is given by x is equal to say a sine omega t, right? So at any future instant of time, the signal value can be exactly predicted. So there can be other signals like periodic signals, transient signals. For those signals also, the future values of the signal can be predicted exactly. However, there are signals in which it is not possible to predict the exact value, precise value of the signal in future instant of time. For example, if a bicycle is moving on a rough road, then the vibration of the bicycle due to the roughness of the road cannot be predicted at a future instant precisely, right? Because the roughness of the road is random and that leads to random vibration of the bicycle. So therefore, the random signal does not follow any specific law by which it varies. That is why the random signal cannot be quantified by any deterministic law. While we use average values and other statistical measures to quantify the random signal, right, the characteristics of the random signal, and the future values of the random signal cannot be precisely predicted, but can only be predicted in probabilistic terms. So now, is it possible to obtain the frequency domain representation of a random signal? So random signal is an aperiodic signal because it does not repeat, right, and therefore we cannot use Fourier series expansion to represent the signal in the frequency domain. For example, earlier we studied that Fourier series can be used to represent the frequency domain representation of a periodic signal, right, in the frequency domain, right. But because random signal is not periodic, it is an aperiodic signal, we can't use Fourier series expansion. Now the random signal is also not a finite length signal. For example, if we have a impact made on the structure, so it is a finite length signal, right, or the oscillation of structure due to impact, that again is a finite length signal because after some length of time the vibration completely decays, okay. So these are all transient signals and they are finite length signals, but a random signal is not a finite length signal. It can continue theoretically forever. So if the bicycle is moving on a road which is continuing indefinitely, then the random signal will also continue indefinitely, right. The random signal is also not absolutely integrable. That is, if we integrate the absolute value of the random signal over the complete time axis, that integration is not finite. So it is not absolutely integrable. So such signals which are not absolutely integrable, the Fourier transform does not exist for such signals. So therefore, neither Fourier series expansion is applicable for random signal nor Fourier transform can be taken. So how the frequency domain representation of a random signal can be determined? What frequency components make up the signal? How that can be determined? So for this we define what is called as autocorrelation function, okay. So autocorrelation function of a random signal, right, satisfies the condition for existence of the Fourier transform, okay, as we will see on the next slide. What is autocorrelation function, how it satisfies that condition. So it is seen that the autocorrelation function is absolutely integrable, right. The integration of the absolute value of the autocorrelation function over the time axis is finite. So, let us see what is autocorrelation function. So, autocorrelation function defined for a stationary ergodic random process. A random process whose statistical characteristics do not vary with time, they are independent of time, is called a stationary random process. And when the characteristics of the random process can be determined from one sample function of the random process, then such a random process is also called ergodic, right. Otherwise, we require several sample functions of the process in order to determine its statistics, which makes the process non-ergodic, right. So, many random processes in practice can be modeled as stationary ergodic processes. So, for a stationary ergodic process, the autocorrelation function is given by this expression. Okay. To understand this expression, let us look at a signal first. Let us say this is the signal x of t, right, and let us say this is a random signal of, let us say we focus our attention on length t of the signal, okay. And let us now take the product of two samples of this signal. So, let me use green color here. So, let us say at instant t, this is the sample, and at instant t plus tau, this is the sample. So, these two samples are separated by a time lag tau, right. So, we take the product of these two samples, that is x of t multiplied by x of t plus tau, right, and then we integrate this product over the length t of the signal, right, and the average value of this is obtained by dividing this by capital T. So, this basically tells us the correlation between the samples xt and xt plus tau, which are separated by time lag tau, right. And then if we take the t to be very long in the limit tending to infinity, then this becomes the autocorrelation function of the signal, okay. So, this is the origin of this expression. So, the autocorrelation function tells the correlation, the degree of similarity between samples of the signal separated by time lag tau, right. And if tau is varied, then the obviously the value of the autocorrelation function will change, right. So, let us take an example of a random process, a random signal, and see that what is typically the autocorrelation function of such a signal. So, let us look at random signal and its autocorrelation function. So, we see from here that now we have on the left side in the part A of the figure, we have the random signal, right, x of t, and the autocorrelation function of this random signal is shown on the right, that is figure B. As tau is changing, the autocorrelation function is also changing, and we see that for tau is equal to 0, right. So, this is the autocorrelation function R x x 0, right, that is when tau is 0, the autocorrelation function is maximum, and that is expected because if the time lag between the sample is 0, then basically we are finding the similarity of a sample with itself, right. So, all samples they are perfectly correlated with themselves, and that is why the autocorrelation function is maximum for tau is equal to 0. But when tau is non-zero, it is increased, then what happens? Now we are looking at autocorrelation function or degree of similarity between two samples which are separated by time lag, and then the degree of similarity then would depend on tau. And we see from this figure that as tau increases, the degree of similarity or correlation between the samples reduces for a random signal. So, smaller the tau, higher is the value of autocorrelation function, higher the value of tau, smaller is the value of autocorrelation function. And in fact, as tau tends to infinity, the autocorrelation function tends to 0. Therefore, the conclusion is that the autocorrelation function of a random signal is a decaying signal. It is a signal which decays with time, right, and therefore it satisfies the condition for existence of the Fourier transform. Okay. We saw on the previous slide that autocorrelation function is absolutely integrable. So, we can that is now clear from the figure on the right hand side, right, because the autocorrelation function is decaying, it is absolutely integrable. The integration of the autocorrelation function over the time axis will be a finite quantity, it will not be infinite, and therefore the autocorrelation function of the random signal satisfies the condition for Fourier transform. So, it means though we can't take the Fourier transform of a random signal, or the Fourier transform of a random signal is not defined, the Fourier transform of autocorrelation function is defined. So, now but the important question is that does the Fourier transform of the autocorrelation function give us or tell us anything about the Fourier transform of the random signal, or the frequency domain representation of the autocorrelation function, does it tell us anything useful about the frequency domain representation or frequency components which are present in the random signal? So, that is an important question. So, to answer this question, let us look at the autocorrelation function of a sine signal. So, let us take the signal x of t, which is a sine omega naught t plus theta, right. Now, we can find autocorrelation function of this sine signal using the expression for the autocorrelation function we saw on the previous slide, and that autocorrelation function turns out to be this, that is r x x tau is equal to s square by 2 cos omega naught tau. Okay. So, what is the conclusion from here? The conclusion is that the signal was a sine signal and of frequency omega naught, and what we get is a cosine signal of frequency omega naught. So, therefore, the frequency of the autocorrelation function is same as the frequency of the signal, right. So, that is the first important observation. Another conclusion is that the phase of the signal does not appear in the autocorrelation function of the signal. The phase theta does not appear in the autocorrelation function. Okay. So, the phase information of the signal is lost in the autocorrelation function, and then the amplitude of the autocorrelation function is the mean square value of the signal, because a is the amplitude and s square by 2 is the mean square value of the signal. So, these are the observations, right. So, therefore, if you plot the harmonic signal in its autocorrelation function, it would look something like this. So, we can see that the signal here is a sine signal, right, but the autocorrelation function is a cosine signal, okay, but both have the same frequency. That is an important observation. So, therefore, what can we say about the autocorrelation function frequency content? So, what is the frequency content of autocorrelation function? So, the frequency components in the autocorrelation function are the same as in the original signal. So, on the previous slide we looked at the autocorrelation function of a sine signal, but if we take a periodic signal, okay, so the periodic signal consists of many harmonic components, right, because that we know from the Fourier series expansion, and therefore, the autocorrelation function of the periodic signal will be the sum of the autocorrelation function of the individual frequency components, and therefore, the autocorrelation function of a particular frequency component would be at the same frequency as the frequency of that component, right. So, therefore, we can say that the frequency components in the autocorrelation function, they are the same as the that they are in the original signal. So, that is important. So, this says that the frequency composition of the autocorrelation function tells us the frequency composition of the the signal, parent signal. So, therefore, the autocorrelation function preserves the frequency composition of the signal, and hence it can be used to study the frequency composition of the original signal. But as we saw that the phase of the harmonic components, they do not appear in the autocorrelation function. So, the phase information of those functions, different frequencies is lost in the autocorrelation function. So, now we can therefore take the Fourier transform of the autocorrelation function, and the Fourier transform of the autocorrelation function is called spectral density or autospectral density. Okay. So, you can see this is the expression for the autospectral density S x x omega, and that is nothing but integration over minus infinity to plus infinity of the autocorrelation function r x x tau into e to the power minus I omega tau into d tau. So, that is by the definition of the Fourier transform. So, this is the autospectral density, right. So, this is ASD, autospectral density. Similarly, we can determine the autocorrelation function itself from the spectral density, right, by taking the inverse Fourier transform of the autospectral density. So, therefore, autocorrelation function and autospectral density, they are related by Fourier and inverse Fourier transform. Now, the autospectral density is also called power spectral density, because it can be shown that the area under the PSD curve or the ASD curve is nothing but the mean square value of the signal. Okay. So, if we take the area under the PSD curve or the ASD curve, then that is the mean square value of the signal x of t. So, autospectral density is a continuous function of omega, it is not discrete. So, if we take the autospectral density value at a particular value of omega, then that will tell us the power of that component, but that power will be infinitesimally small because the autospectral density is a continuous function. So, that is why the autospectral density has the units of, if the let us say x has the units of meters, then the unit of autospectral density is meters square per hertz. So, therefore, autospectral density at a certain value of omega or frequency tells us the power of the signal in a frequency band of 1 hertz, right, around that frequency, right. So, it uses the density of the power, that is why it is called power spectral density. Because the autocorrelation function loses the phase information, and therefore, autospectral density has also only magnitude, but does not have any phase, okay, it does not have any phase. So, in practice what we measure is a discrete signal. So, x of t is the actual continuous analog signal we want to measure, but after measurement we have discrete signal x of n, right. So, therefore, we need to determine the Fourier transform. If let us say x of n is random, then we need to find frequency domain representation of a discrete random signal, right. So, basically what we are talking about is autospectral density based on a discrete signal. Now, because signal is discrete, therefore, the autocorrelation function of the signal will also be discrete. Therefore, if we want to find the Fourier transform, we will be finding out the DFT of the signal, okay, DFT of the autocorrelation function. So, therefore, the DFT of the autocorrelation function uses a discrete spectrum, and that spectrum is referred as SXXK, which is a discrete spectrum of the autocorrelation function. So, therefore, this spectrum is no longer continuous, it is a discrete spectrum, and then it can be shown that this SXXK, which is the discrete spectrum or referred as auto spectrum, is the product of x star k and xk. So, what is xk? Xk is basically the DFT of xn, correct. So, let us try to look at the whole process. What we have got is, first of all, the signal x of t. So, this signal is a continuous signal, random signal, and after discretization what we get is a discrete signal xn, right, and this signal therefore will be of this form, it is a sampled signal like this, okay. So, it will be a discrete signal. So, now we can find the autocorrelation function of this, that would be Rxxr, right, where small r is the sample number. So, we can find a DFT of this x of n, and that gives us autocorrelation function, and then we can find the, so therefore, this is we can then find the DFT, and this then would give us the auto spectrum of the signal, auto spectrum of the signal, right, or which is the DFT of the autocorrelation function. But the other way to obtain the auto spectrum is that instead of finding the DFT of the autocorrelation function, or instead of finding the autocorrelation function first and then finding its DFT, we can directly find the DFT of the sample signal, which basically will give us xk, right, and then we can find the Sxxk directly from xk, right, which is given by the complex conjugate of xk multiplied by xk, okay. So, either process can be used, but generally we follow the later process, in which we directly find the DFT of the signal and then find the auto spectrum by this relationship. Therefore, what we note is that the auto spectrum is a discrete version of the spectral density, it is a discrete version of the auto spectral density, okay. So, it is a sample version of the auto spectral density. So, therefore, that way they are related. So, now what about if we have two different signals, we have two random signals instead of one random signal. Let us say we have a random signal x and random signal y. So, extending the definition of autocorrelation function for a signal, we can find a correlation between two different signals, and that is called cross correlation function, right. And the cross correlation function again for a stationary ergodic process is defined by this relationship. So, now here we have now one signal, let us say this is signal x, right, like this, and then we have another signal y, okay, like this. And then what is cross correlation? Take a sample from the signal x at instant t, right, and then we take another one sample from signal y at instant t plus tau, right, and then we take the product of x of t and y of t plus tau, okay, and then we find the average value of this product over time length t such that t is very large. So, that gives us cross correlation function between x and y. So, the cross correlation function tells us the degree of similarity between the samples of signal x and y which are separated by time lag tau, okay. So, now the question arises, what is the frequency domain composition of cross correlation signal? What are its characteristics? So, it is seen that the frequency components common to signals x and y, they show up in the cross correlation function, right. So, the frequency components which are common in x and y, only they show up in the cross correlation function. If there is a frequency component in x which is not present in y, then that does not show up in the cross correlation function, okay. Also, the phase of a frequency component in the cross correlation function, right, is the difference between the phase of that component in the two signals, right, and therefore, the cross correlation function basically preserves the relative phase between the common frequency components in the two signals, okay. So, therefore, the cross correlation function not only has magnitude, but it also has phase, and the phase of a component frequency phase of a component in the cross correlation is the relative phase between the corresponding component in the two signals. So, this is very important because this helps us to also retrieve the phase information between the signal. Autocorrelation function does not have phase information, but the cross correlation does have the phase information between the signals. So, now we can extend the definition of spectral density to cross correlation function and define what is called as cross spectral density CSD, which is the Fourier transform of the cross correlation function, and it is given by Sx y omega. So, this is CSD, right, which is the integration of r x y tau into e to the power minus I omega tau d tau over minus infinity to plus infinity. This is the whole time axis. So, that is the cross spectral density, and similarly we can retrieve the cross correlation from the cross spectral density by inverse Fourier transform. So, cross correlation function and cross spectral density are related by Fourier and inverse Fourier transform relationships. So, as we said that cross spectral density has both magnitude and phase. So, now we can define what is called as cross spectrum, because if the signal is discrete, right, if the two signals x and y are discrete, then we can find the cross correlation between them, and that would also be discrete, and then finding the DFT of the discrete cross correlation gives us the discrete spectrum, and that is called as the cross spectrum, okay. So, SXY is the cross spectrum. So, this is cross spectrum, okay, which is basically the DFT of cross correlation function. And again it can be shown that Sxyk is also equal to the product of x star k, which is the complex conjugate of DFT of x of n, multiplied by yk, which is the DFT of signal yn. Okay. So therefore, cross spectrum is a discrete version of the cross spectral density. In this way, the frequency domain representation of random signals can be defined using auto and cross spectrums. Let us see that how we can determine the frequency response function using these estimates. To find FRF, what we do, we apply random input to the structure and then we measure the response, which also is random. So we have this, say, system, and then we apply a random input to this random force f of t, and it generates a random response x of t. So this x of t could be displacement, velocity or acceleration. So therefore, in this case now we have two signals, random input and random output. So now we can determine the auto spectrum and cross spectrum with respect to these signals. So also the spectral densities we defined, they are two-sided spectral densities, but in practice often we work with one-sided versions of these spectral densities. So let us say GFF omega is one-sided autospectral density corresponding to two-sided autospectral density as FF omega. So therefore, this is the autospectral density of the input force, input random force that is being applied. Then we can determine the autospectral density as Fx, which is the spectral density between the force and the output response x, and that is two-sided, and let Gfx omega is one-sided cross spectral density corresponding to two-sided cross spectral density as Fx omega. And then we have earlier defined the FRF estimate H1, right, which is the ratio of Gfx and Gff. So for the random input and output, we can determine Gfx, Gff, and then determine the frequency response function estimate H1 from this relationship. And then we can also determine the estimate H2, which is the ratio of Gxx, which is the autospectral density, one-sided autospectral density of the output response x, divided by Gxf, which is the one-sided cross spectral density between the response x and the force f. So that gives the estimate H2. So in this manner, therefore, even by applying random input, right, we can obtain the frequency response function. We can estimate the frequency response function of the system. In this way, today we looked at FRF estimation using random signals, and we defined the auto and cross correlation, auto and cross spectral density, and auto and cross spectrum. And then we saw that how FRFs can be estimated from auto and cross spectrums. Now we stop here. Thank you.